we've seen a bunch of this already, but now we're going to highlight some things to formally put it into our notes to look a little bit at the notation that's involved in combining functions graphically. So if you have two graphs and you wanted to add them together, we've already seen the strategy of taking nice points and you can add your y values together. So if you look at the points they've labeled here, on the red graph they have 2, 2. On the blue graph they have 2, -1. If you added those together, you would get the point 2, 1, because 2 plus -1 is 1. So if we add our points along the way, take a bunch of nice points, we can get an idea of what the shape of that graph is. Now, notation-wise, we're mostly going to see it written this way, f of x plus g of x. However, you can also see that same thing written this way. And that's, for whatever reason, that is more confusing. If you see f plus g of x, I would suggest just taking the time to write it in the form f of x plus g of x. It's just easier to work with. Because you will get questions I've seen on the exam. If they gave you f of 2 plus g of 2, you'd be like, that's easy. From the red graph, f of 2 is equal to 2. From the blue graph, g of 2 is equal to -1. If I was adding those together, I'd get 1. But I've also seen it on the exam written like this, and for whatever reason, that makes it harder. It just looks different. You're not as used to it. So when you see this, f plus g of 2, I would say take a first step and just write it in the form that you're more used to, and then you can work with that from there. So after taking a bunch of nice points, we get that graph. Now, something about domain and range. Your domain of your red graph there is x is bigger than or equal to 2. The domain of the blue graph is everything, but when you add functions together, your domain will be only where the domain exists for both functions. So only where the domain overlaps. So the domain for our green graph is also x is bigger than or equal to 2, to -2. So adding functions, what do? We find nice points. We add the y values together to add those graphs. We plot those points and get an idea of what the final graph will look like. Sometimes you can think about the original functions. Here we have a square root plus a line. That's not something that we ever graphed in transformations, so we don't really have an idea what that graph looks like. So our best guess is just to do a bunch of nice points. And as you can see from the green graph, it's kind of an interesting. Yeah, what the line does is it sort of rotates your square root graph. Second one, subtracting functions. Again, notation-wise, it's the same thing. You can write it as f of x minus g of x, or you can write it as f minus g of x. Again, we look at the y values, and now we're going to subtract. So if we find a bunch of nice points and do that, right, here, 2 minus a -1 would give you 3. Plot a lot of points. Once again, you have to consider the domain only where the domain overlaps. And the overlapping domain is going to be true for adding, subtracting, and for multiplying. We're going to look at dividing a little bit later because dividing has some non-permissible values, which adds another level of complexity to it. But for adding, subtracting, and multiplying, you have to look where does the domain overlap. So finally, in looking at multiplying here, again, notation-wise, you can have it written both of those ways. If you take your nice point and look at what happens to it, multiply your y values, -1 times a 2 would give you -2. Some other really nice points for multiplying is find out whether either of your original functions were 0. So here my red graph is 0. 0 times anything will be 0. Here my blue graph is 0. 0 times anything is 0. So those are going to be nice points to use when multiplying two functions together. Again, the domain is going to be where they overlap. So let's look at example 1. Here we have two functions, a line plus an absolute value function. State the domain and range of both. Write an explicit equation for adding and an explicit equation for multiplying. So part A, for f of x, your domain is everything. For g of x, our domain is everything. That's telling us that if we add, subtract, or multiply, our domain will be everything for those as well. For part B, if we were adding, this is asking for an explicit equation. So an explicit equation means that you want to write an equation with only x's. Right now, this equation right here, this is not an explicit equation because it's written in terms of functions. So an explicit equation would mean you want to write an equation just in terms of x. So what we can do is we can start off by saying, well, h of x is just f of x, and f of x is x plus 2, plus g of x, and g of x is the absolute value of x. So all I need to do is add those two together. If I take off the brackets, is there anything I can combine? Not really. There's no like terms. You can't add the absolute value of x with the x in this case. So right now, to determine domain, we already knew that the domain is going to be everything. There's no non-permissible values here. Okay? So our domain is everything. Now to figure out our range, we're going to have to, maybe we're going to have to graph this. We're going to have to think about the equation a little bit to see what happens.
I noticed that whenever it's negative,
Mm-hmm.
the absolute value of x will always be possible to actually cancel out, so it will stop at 0, just go along 0.
It's going to go along at 2. Yeah.
Go along at 2, yeah.
So
Sorry.
one thing to notice, so if we started to graph this graph, if we started to take some nice values or just plug in some values of x. So that's sort of what nice values is, sort of like plugging in a table of values. And what Peter said is whenever I put in a negative number for x, if I put in -5 for x, can you see that there would be a -5 here, but the absolute value would make this -5 into a +5? And we would get those to cancel out. We would just get 2. If I put in a -3, I would get 2. If I put in a -1, I would get 2. So when I go to graph this, every negative number that I put in is always going to be 2. If I put in any positive number, it's going to be, like if I put in 1, I'm going to get 1 plus 2 plus 1. I'm going to get 1, 4. If I put in 2, I'd get 2 plus 2 plus 2, I'd get 2 comma 6. If I put in 3, I'm going to get 3 comma 8. What does it appear to be making? A line. Wow, that's not green. There we go. So our graph looks like this in the end, and once we've graphed it, we can say our range is bigger than or equal to 2. Now, it would have been hard to just look at our equation and see that is true. Now, sometimes what people do in a situation like this is they say this graph seems to be 2 separate lines, 2 different parts. And it seems to equal 2 when x is less than 0. And it appears to equal a line with a slope of 2 and a y-intercept of 2 when x is bigger than or equal to 0. Now, I'll put a comma here in between. This is something that is called a piecewise function. And it's called a piecewise function because the graph is 2 different equations that you know or recognize, and it comes in 2 different pieces that get joined together. So one piece is the line y equals 2, and that only happens when the domain was less than 0. And the other piece was the line 2x plus 2, and that happens when x is bigger than or equal to 0. So that's just something to notice here. We weren't asked to write that equation out, but now that we've got the graph, by plugging in some nice values, we can see that that's what that's equal to. In part C, we're multiplying now. So it says, what is an explicit equation for p of x if you were multiplying? Well, multiplying, you would have started with x plus 2, and you'd multiply by the absolute value of x. This would be an explicit equation by putting those 2 together. If we were trying to find the domain and range, well, we already know that there's no non-permissible values. So our domain is everything. But if we look at what happens when we multiply things together, do some nice values, like if you plug in 0, you would get 0. If you plug in 1, you would get 3. If you would plug in 2, you would get 8. What happens when I start plugging in some negative numbers? If I plug in -1, I get 1. If I plug in -2, well, that'll make that 0. That will be 0. And if I plug in -3, this will be 3, this will be a -1. Now, looking at those points, seeing points in that way, you might say, hey, that looks like an x cubed graph, Mr. JR, because that's how I know points to act like that. And you might think that it would look like an x cubed graph by how the points are. This graph, when it's drawn in its end, almost like an x cubed graph, but it has a sharp point in it. It's a little bit different. So what are these graphs? These are actually 2 different parabolas. This is a piece of one parabola, and this is a piece of another parabola. To figure out what those parabolas look like, if I were to write, here, first of all, we'll just finish this question. Our range is everything. One way to figure out what the equations of these parabolas are is to understand a little bit about the absolute value of x. You know what the absolute value of x does. It makes whatever is positive stay the same, and whatever is negative, it makes positive. So the absolute value of x is sometimes written as a piecewise function, because when you plug in something bigger than 0, it stays the same, right? Even bigger than or equal to 0. But when you plug in something less than 0, you have to multiply it by a negative to make it positive. Like if I plugged in -3 into the absolute value, it's +3. One way we could show that is breaking it up into two parts, saying that when x is bigger than or equal to 0, it's just x, same thing as what you see inside. But when x is less than 0, like if it was a -5 inside those absolute value, you have to make it positive, and one way you could make it positive is by multiplying by a -1. So considering that, if I wanted to write my piecewise function for this graph, for h of x, or sorry, p of x, it has two parts. It has a part where x is bigger than or equal to 0, and a part where x is less than 0. Maybe I'll move those farther that way. When x is bigger than or equal to 0, if you look at our equation, what happens to the absolute value? What does it act like? It acts just like an x. And so if this was just an x and I distributed it here, I would get x squared plus 2x. And when x is less than 0, what does my absolute value act like? Acts like a -x. So if I would distribute that, and I have two parabolas. Here's the one parabola pointed down. Can you see that the part of that graph that you don't see would keep going like this, but we don't draw that part? And can you see that the part of this parabola that you don't see would have gone like that? But then they just get pieced together. Usually on the exam, the absolute value is a little bit harder to work with. So I would say generally on the exam, they avoid some of the absolute value. But it's here, so I have a little bit of an idea how it works. Questions for practice after this one are 3, 5, and 10.